Welcome to another chemistry video. By the time you finish this, you should be able to draw Lewis structures for molecules that have single, multiple, or both types of bonds in them. Okay, let's start out talking about electron dot notation. If we look at elements, the atoms of them singularly, we need to know how many valence electrons each one has. So electron dot notation is a way of drawing that. This sulfur, for example, we know that it has 6 valence electrons, so we're going to draw the symbol for sulfur and 6 dots around it. Nitrogen has 5 valence electrons, so we symbol for nitrogen and 5 dots around it. Magnesium, 2 valence electrons, so 2 dots. And so you're probably wondering, well, how the heck does he know that? Well, there's actually a pattern to this. I've created this table here, which you may or may not need to copy down the whole thing. The number of valence electrons can vary from 1 to 8. Noble gases have 8. And there's a pattern to how this works. Group 1 on the table, the columns, the groups. Group 1 has 1 valence electron. Group 2 has 2 valence electrons. Skip the transition metals. They do all sorts of weird things. So Group 13 has 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. Group 16 has 6. Group 17 has 7. And group 18 has 8. Now, looking at that, you're probably going to be able to pick up that pattern pretty easily. And if you do, that's going to help you out as we move further along in bonding. This column here, electron dot notation, I've just created a fictitious element X, we'll call it. And I've shown you how in group 1 you would put the element symbol and 1 dot next to it because it has 1 valence electron. Here's an actual example. Lithium is from group 1 and has 1 valence electron, so 1 dot. Here our element X is 2 dots because it has 2 valence electrons from group 2. So magnesium, an example of that, 2 valence electrons. And you can see how they fill in as you go down the table. Now, when you get to having 5 or more, the electrons start showing up as being paired on one side or on both sides. This matters in the future when we start putting together Lewis structures. This is going to matter. Make sure that, like number 18 here, we've got 2 of them on the left side of the element symbol, 2 of them on the right side, 2 on the top, 2 on the bottom. They have to be paired. And as we get into Lewis structures, you'll see why. Okay, the octet rule in bonding. Generally, atoms are going to bond so that they have 8 electrons. That's where they're most stable. Nature favors stability. You get ripples in a pond. The little waves or ripples will keep going until they get calm and there's nothing, there's stability there. Atoms are the same thing. They'll bond to where they're the most stable. Generally, that's 8 electrons. Their valence layer has 8. And they'll share, they'll give electrons, whatever it takes to make this happen. Now we're going to draw these so that they have 8 electrons using what's called a Lewis structure. And that's a diagram where you use the atomic symbols, just like we had before. And we have dots for unbonded electrons, just like you saw in the last slide. And we also have a way of showing bonds, how atoms are bonded together. And types of bonds include single bonds, where you'll have 2 dots and it changes to a dash because the 2 atoms are sharing an electron. Multiple bonds could be double bonds or triple bonds, and it's when they share 2 electrons, so we've got 2 sets of dots turn into 2 dashes, 3 sets of dots turn into 3 dashes, or a triple bond. If you don't get this yet, don't worry, you will. Okay, Lewis structures, how to draw them. There's actually 5 steps. Again, you may want to jot this down. We're going to go over each of these steps in detail. First, you calculate the total valence electrons, TVE. Next, you determine the Clark number. I'll show you how to do that. Then you take the Clark number and subtract total valence electrons. You draw your compound skeleton, which is the element symbols with all the bonds and the correct types of bonds. And then you fill in the remaining non-bonded electrons to form octets around each atom. So here we go. Let's do these steps. Our first step is to find the total valence electrons. Hydrogen, each hydrogen has 1 electron in its valence, it's group 1. So there's two of them. Total valence electrons here is 2. Fluorine, we have 2 of these. Each fluorines are in group 17, so each one has 7. 7 times 2 gives us 14. Okay, here we have a carbon. Carbon has 4 valence electrons. It's in group 14. Each hydrogen has 1. 4 plus 3 is 7. Iodine, group 17 again, so 7 plus 7, 14. Okay, nitrogen and oxygen. Nitrogen's going to have 5 because it's group 15. Oxygen will have 6 because it's group 16. 5 plus 6 is 11. You probably get how this works. Water will have 8. Here we're going to have 10 for nitrogen, 30 for the, that'll be 40. So you kind of get how this works now. Pretty simple step. Step 2, Clark numbers. We use a simple formula to determine a Clark number. Don't worry about what the Clark number is just yet. Just let's figure out how to find a Clark number, and then I'll show you in the next step or two what that's actually used for. The formula is to find the Clark number is 6 times Y, and Y stands for the number of atoms in our molecule or our compound, but we don't count hydrogens. Okay, plus 2. All right, so here we have our same examples again. 1 nitrogen and 1 oxygen, so that's 2 atoms. So our Y is a 2. So 6 times the number of atoms, 2, plus 2 gives us 14. Water. Okay, here, remember, hydrogens don't count. So we only have 1 atom that we're going to use in this equation. So 6 times 1 plus 2 is 8. Okay, here we have 1 phosphorus, 3 fluorines, so we have 4 for our value of Y. So we have 24 plus 2 is 26. I think you kind of get that. Let's move on. Step 3. Step 3, we're going to take our Clark number minus the total valence electrons. Now, all this stuff written in here doesn't make sense just yet, so I'm going to come back to it. Let's go to the next slide, and then I'll come back to this one. So we take our total valence electrons, 11 for nitrogen and oxygen, and our Clark number, 14. We've already calculated these. So the Clark number, 14, minus the total valence electrons, 11, gives us 3. Now, 3 means, here's the slide I said I'd come back to, here, positive 3, means that when we bond together nitrogen and oxygen, we have 1 double bond and the rest single bonds if needed. And 1 pair, excuse me, 1 unpaired electron, a free radical. We'll get to what that means in a minute. So we have a double bond in there. When we bond these two together, it's a double bond. Why don't I jump ahead so I can kind of show you what that's going to look like when I draw it. Okay, here's nitrogen and oxygen. I'm on the step 4, and I'll go back to do the others. Nitrogen and oxygen, 1 double bond. Nitrogen, double bond, remember 2 dashes? So this is our compound skeleton, or also called our structural formula. It's a kind, number, arrangement of bonds, but it doesn't show the electrons yet that aren't used in bonding. Okay, so let's back up again. Look at another one, water, H2O. We already found the total valence electrons, and we found the Clark number. Each was 8. 8 take away 8 is 0. So 0, what does that tell us about our bonds? Go back here, here's 0. All single covalent bonds. So when we go to our compound skeleton here for water, oxygen's in the middle, single bond to each hydrogen. Hydrogen will only ever have a single bond because when it bonds it only wants 2 electrons and it only has 1 to share anyway. So hydrogens are kind of a gimme in that respect. They'll only ever have single bonds to them. Okay. Now if we go back again, you guys can work through these on your own, and feel free to stop the video, work through these on your own, grab the total valence electrons and the Clark number, find the difference, and then go back to here and you can find out exactly what kind of bonds you should have in your structural skeleton. Now I'm going to go ahead and I'm going to click on, here we have this one, we have this one. I'm going to click on these two and uncover them. So if you don't want to know the answer, stop the video here if you want to figure it out yourself. This right here, this is what your structural skeletons should look like. All your bonds. This one right here, you might find you're going to have to play around with a little bit to get it to work out. because nothing, you can't have an element with more than 8 valence electrons. Okay, so let's move on to our last step. We had our structural skeleton all worked out, and we need to look at our total valence electron again for each of these to figure out, well, how many electrons do I have left to put in place? Remember nitrogen and oxygen with the double bond? Well, we fill in the rest of our electrons. We've got 2, 4, 6, 8, 10, 11. This one here is kind of an oddball. Remember when we had our chart way back here? And we came up with a 3, one double bond, the rest single. We didn't need those. One unpaired electron. That's called a free radical. This is kind of a unusual case. You won't see this a lot, but right here, this missing electron, that makes it a free radical. This one right here, you take that structural formula, that skeleton, and now you're going to add in the rest of your electrons that are unbonded. So we've got 2 here, 4, 6, 8, and the phosphorus, I already had the 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8. Okay, so it looks like I'm missing a couple of dots here. Oh man. Let's count these up and make sure I've got it right. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Sure enough, I need to have 2 more electrons right here on the phosphorus. So 1 here, 1 here. So now we have a total of 26. Good thing I counted on that one. Okay, and here's the other one. Here's water. Unbonded electrons, we had 2, 4, 6, 8. And this one right here, the big beast, you count that up, and that will be 40. Now, when you're checking these out at the end, make sure that each atom has 8. So it's supposed to have 8. And also make sure that you have a total of 40. So when you get done, to make sure you have it right, go around and count each one. This nitrogen's 2, 4, 6, 8. You count this nitrogen, 2, 4, 6, 8. Over here in oxygen, 2, 4, 6, 8. Okay, you kind of get the idea. You can do that with each one. And also count the total and make sure you have 40. Okay. Special cases. We only have 3 of them. The first one I've already talked about, a free radical, substance with 1 unbonded or unpaired electrons. Resonance. Okay, now this is kind of a weird case where you can draw stuff more than one way. Like an O3, it's ozone. That can be drawn more than one way. It can be drawn 2 different ways. You could have a double bond on this side and a single over here, or you could have a single on this side and a double over here. Now if you play around with SO3, that can be drawn 3 different ways because it also has double and single bonds, and they can be turned different ways, drawn in different ways, and that's referred to as resonance. Our last unusual case, I guess it's not that unusual, it's called ions. Atoms are compounds that have an overall positive or negative charge on them, and we'll cover ions in greater detail in the future, but you're going to draw your Lewis structure just like you did before. But if something says it's an ion, in this case it'll have I did this carbon, this compound right here. There will be brackets and it'll denote the charge on it. This one is 1 minus charge, 2 minus charge, 3 plus charge, so on. So we've got this nitrogen NH2 as a negative, so that means it's a 1 minus. It has 1 extra electron. This NH4 has a plus, so it's missing 1 electron, makes it overall charge positive. The CO3 has a 2 negative, so it has 2 extra electrons. So when you get done putting this Lewis structure together, you're going to have to add in these 2 extra electrons as you go through, and you put brackets around this whole thing, and you put that same charge, just like we had here. This 2 minus has to go up in the top left corner. Okay, thanks for watching.